Okay, so welcome back for week two. Um, yeah, I didn't scare that many people away. That's good. Okay, one or two. But hopefully they're at home streaming because it's cold. Okay, so let's do a quick review of the slides. Hopefully you all got a chance to look at them. Um, so we'll do a quick, just gloss over the slides, and then we can do Q&A afterwards, and then we'll get into the code. This time there will be no fill in the code, so that's fun. It will be more just kind of playing around with it, tuning the model, trying to understand some of the pain points that you can get when you're doing this. Okay. All right, so we're talking about anomaly detection, and I preceded this by talking about how traditionally anomaly detection is based with numerical features, continuous features, stuff that is on some kind of scale. This is bigger than this is smaller than that. So you can create some metric space, and then you can come up with a threshold and a measurement for this is normal, this is abnormal. And then I gave some examples, some of which you're probably familiar with. A lot of people seem to like isolation forests these days. Everybody seems to talk about autoencoders, but I think they're pretty useless for anomaly detection, cluster analysis, that kind of thing. Okay, so anomalous events are a lot more tricky, especially when you're dealing with categorical data. This is because we have no metric space to compare things. So is Bob's computer more dangerous than Alice's iPhone? Is what's weird about an apple versus an orange? Like, these are all things that we have no way of quantifying risk or anything else associated with these things. And you might even be tempted if you saw a numerical value to do that, but that doesn't really make sense because it's just our lazy way of pigeonholing things and saying you're going in this box, you're going in this box. Okay. So an example of an event could be a person logging on a particular day from a particular IP using a particular device at a particular time to a particular service or server. So how do we try and get some values out of this? Can we get some vector representation? Or how do we get a model, at least, to learn that this is normal, this is abnormal? And this can be very easy if you've got labels, because then you can just do whatever classification you want, and there you go. But if you've no labels, then it's a little bit harder. So this is where self-supervised learning comes in. It's that kind of weird in-between unsupervised learning and supervised learning. We don't have explicit labels. So somebody hands you the data, but there's no labels associated with it. You have to create your own. So they come from the data. And then you ask a model to perform certain tasks according to these labels. So you have to make sure that the task is intelligent. You have to make sure that the data is intelligent as well. So an example, this can be applied to any kind of data medium that you're interested in. So images, you could be saying like, well, predict the rotation or fix the rotation of this image, or where does this patch of the image go in relation to this patch? Sequences, one of these frames is out of sequence, where does it go? Or is this going forward, or is this going reverse? Text is a huge one, where you've got word embedding, sentence embedding, so BERT, things like this, which everybody talks about, so you're probably familiar with those. And it can be even applied to tabular data, which is what we're going to use today. Graphs also, for sure. So when you're learning about graphs next week, consider applications of self-supervised learning to graphs. So an example here is the picture of a cat. So here, this is all about trying to learn, do representation learning on images, but you're not doing it with any labels. So given this center image from box 5, where does this ear go with respect to that one in these other 8 boxes? And you might notice that there's a gap between every one of these boxes, and so that's to stop the model from cheating and going like, well, this line matches up with this line. That's where this should go. So I bet you anything, when this guy or woman was creating this paper, they probably didn't do that at first. They probably just partitioned off the image in just 9 even blocks and then thought they were doing great until someone pointed out it's cheating. So that's probably, a very familiar feeling for you guys in your lives, where you realize that, oh, the model's doing great. Oh, no, this is why. This is especially important in self-supervised learning. You really have to be careful that there's not some other way that the model is cheating. Here's another example. It was just about videos and correct ordering. Word embeddings are a great example. So we kind of preface a lot of the work talking about word embeddings here. But really, it's all about trying to figure out a vector representation for words, but by using context for those words. So what are the words that surround? So what's the company that the word keeps? So then you can learn this vector representation, and then some vectors, words that are similar to each other are going to be close by in the same vector space. And you're also going to have kind of relational things, as we're going to see in a little bit. So you can say that the vector, you can take the vector man, add a vector royal and bring it over to king, add the vector female, bring it over to queen, subtract the vector royal, and then you're at the vector for woman. So there's this kind of relational structure that you can have between the words in this embedding space. So how do you do this? So this is why I got a D in art. So we have the cat sat on the mat is the sentence that you all know, but in this case the model has to guess what is the word that goes here. So is it the cat? Is it a planet? Is it a cookie? So you could build a classifier with as many classes as there are words in your vocabulary, but that means that your softmax is going to blow up. You've got like 50,000 words in your vocabulary or something like that. Well, good luck making sure that that is a nice, smooth-looking distribution. That's just going to be a noisy mess. So maybe there's a better way. So you can talk about noise contrastive estimation. So you can either have the model decide, is it the cat that sat on the mat, or is it the planet that sat on the mat? Okay, so that's a lot easier for the algorithm to decide. But you want to make sure that you're giving something challenging, right? So here it's still a word. Okay, you're not just giving it random characters, because that is way too easy. That's just pure noise, and it's not following the distribution of the data. This is probably the most important slide in all of this. I know it looks like squiggles, but I really want to emphasize how important it is that your negative samples are coming from the same distribution, but just slightly perturbed, okay? That, you know, it can't be noise, because it's just going to be way too easy for the model to discriminate against. Okay. So this is just more or less the pseudo algorithm. So for a given event, you're going to randomly select a feature. For that feature, you're going to randomly select a new category. So replace Monday with Saturday. And you're going to do this lots and lots of times for all of the samples. And then you're going to classify real and fake data. Okay? And then, yeah, you test it on your test data to determine anomalies. So there's a lot of things you need to consider when you're doing this. Negative sampling rate is one thing. The real idea being here that it just reinforces the normalcy of the true data. There is a mathier argument, which I'm not going to get into, but there is a paper, which if anybody's interested, I can link you to, that goes into this. Some features you might not want to vary. You might want to keep them fixed, or you might want to throw out altogether. You might want to change your sampling procedure. Maybe you're interested in finding the most probable substitute or the least probable, or just doing a uniform substitution. Hard negative mining is a really interesting area. I didn't cover it in the code because I thought that might be a bit too much, but it's something that if you're interested in, it's not a whole lot of work to implement. But really, it's all about coming up with the most challenging examples for the classifier. So here's an example of the negative sampling rate. As you can see, increasing the negative sampling rate tends to push up the area under the curve for the precision recall curve. But you obviously can't go too high because it's just going to take forever to train. Feature selection, so some of these you can keep fixed, some of them you can vary, and some you can remove. You don't need an employee number, but you probably shouldn't be varying the operating system for a given device or process, because that's going to create something that's unrealistic and is going to be very, very easy, again, for the classifier to realize this is not normal, okay? Okay, yeah, so sampling procedure, negative sampling. Yeah, okay. So here's an example that you've got Bob. It's Monday. He's in Toronto. He's on his iPad. He's checking his email, and it's 2 p.m. You could vary everything and have Jerry, the former intern, calling in from Moscow on Saturday at 2 a.m. on Pam's iPhone, and he's accessing the client database, but that is too obvious. There's too many alarms being tripped there, and it's too much of a negative sample. So you're better off just finding one thing to perturb, and you're doing it lots and lots of times. So hard negative mining, I'm not going to go into too much here, but it really is, can you replace some of the negative samples with harder negative samples, or with more negative samples? Take the easy ones out, replace them, keep the hard ones, and rinse and repeat. Okay, right. Limitations of this anomaly detection model are that we're assuming that your training data is made up of normal events. That can be problematic. If it's mostly made up, that's still probably fine. If you've got like a fraud detection model, it's maybe not the best to use it for that, especially if you've got, if it's a really terrible payment system or something, like some payment system from the 90s, then it's probably going to be very easily abused. False positives, yes, they're still a problem. So Bob pulling an all-nighter on a Saturday while at home with his parents for the holidays is probably going to trip a flag. What are you going to do about it? It's kind of weird. So there will have to be some, not only, okay, so you're going to have to pick out the correct threshold so that you limit the number of false positives, but there's also going to have to be some like human intervention at some point to say, no, this is why this happened. There is no temporal coherence. So if a whole bunch of anomalous events occur in the same time, the model is not going to realize that this is more important than it being spread out across time. You could build one. There's a lot of interesting ways you could do that. But you'd have to be very careful in making sure that your anomalous sequence actually made sense, that it was causative, that this next step in that sequence is a logical progression from that previous step. It can't just be random noise. That's, again, too easy for the model to discriminate against. And again, we're only talking about categorical variables, but of course you can do this with continuous variables. Just make sure that you know about the distribution. If, for example, it was a bimodal distribution and you were just sampling uniformly, then you're sampling this in this valley of improbability, and that's not a good idea. You don't want to be sampling a whole bunch of values that would never exist. So you have to take into account the distribution that your continuous values would live in. Okay. Okay, so classifiers. So the papers that I linked in this talk, they're all talking about neural networks and embeddings and blah. But as you all saw, PyTorch it's great, but it's a bit of work. And on top of that, GPUs are not cheap. So deep learning isn't always an option, but maybe you can use another classifier. So today we're going to be using XGBoost. Gradient boosting algorithm is an ensemble algorithm for decision trees. It's amazing. I'm sure a lot of you have used it. If not, I highly recommend it. If you're ever doing any kind of binary classification task, I would use this 10 times out of 10 over a neural network, so long as that was all we were doing, so long as it wasn't something like an image as well. But just tabular data, XGBoost every time. It's a really, really good model or algorithm. Okay, so the data set. Oh my God, the data set. So 60 days of data, 12 gigs compressed. So I don't even know what it is uncompressed. I just blew up my RAM on my laptop a few times. 1.6 billion events in total, 12,500 users, 17,500 computers, 63,000 processes. So we've got logon events, we've got processes when they're getting started and stopped. You've got network flows, you've got DNS lookups, so going outside of the network, you've got the red teaming where you've got your anomalous events. This is a treasure trove of cybersecurity data, and it is a massive pain in the butt to sample. So why is that? Well, you could randomly sample it, but you're going to get a really, really poor understanding of cybersecurity from that perspective. You could sample the whole network, but only for a day or two. But then you're going to get, again, a poor understanding of the day-to-day workings of people on this network. So, in my infinite wisdom, I went for a small subset of the computers that were being used. So I didn't limit the number of users. I only looked at auth events, and I skewed the sampling so that they were all computers that were heavily touched by red teaming. So I made sure that these are the ones that were most affected by red teaming. So you actually can have some guarantee that you're going to have some anomalous events here. If anybody's interested in that code, I can share that at a later point, but it's not in the code today. It's nothing too much for you to worry about. So I filtered down, I think, either 8 or 16-ish, in that range, computers. I think it was 16. And in the code, you're going to filter it down again because it was still too much to deal with. Okay, so yep, I think that's it, more or less the conclusions. You kind of already know. You can use it on categorical data. You're learning a probability distribution for what's real, what's weird. But you have to be very careful in how you create these negative samples, is the main moral of the story. And then week 3, Sir,